Do you like projects that involve a strange premise, hundreds of hours of electronics development, and way, way too much money invested? Maybe mix in a little embedded software development and some home improvement just for fun? And of course, RGB LEDs? If so, I think you're going to want to stick around for this one. I'm Zach, and you're watching Zach of All Trades. A few months ago, we started a remodel of our entire kitchen. Cabinets, counters, floors, backsplash. The whole thing, really. The kitchen has a main counter section with a large sink, but there's also this detached bar area. This has a small sink, an instant hot water dispenser. It's a place ideal for making tea, coffee, perhaps your favorite cocktail. Now, naturally, this needs a backsplash. And since it's smaller and on the other side of the kitchen from the main counter section, we decided to go for something a little more bold. We settled on dark blue glass hexagonal mirror tiles from a big box home improvement store. We brought one home to check it out in the space. So I think this backsplash would look pretty great here as is. But I got to thinking. Each of these tiles is a piece of glass that is painted reflective on all the edges. If I were to add an individually controlled LED to each of these tiles, it would make something of a display on this wall. I pondered this for a while and had another revelation. If I were to add some sort of feedback where I could tell which tile had been touched, I could program interesting effects, things like ripples from where you touch the wall. I could even program the game of Snake and play it on my backsplash. I'm going to guess I'm the only person who's ever said that before. Let's talk about how I plan to do this. The LEDs are the simpler part. I'll be using addressable LEDs. They're known by several names, the most famous of which is probably Neopixels. These are the LEDs that usually make up things like RGB LED strip lighting, panel lights, etc. The actual part numbers are WS2812, SK6812, SK6805, stuff like that. I'm sure there are others. These things come in a wide variety of packages, but they all contain red, green, and blue LEDs, sometimes white LEDs, as well as a digitally controlled constant current driver. I actually bought around 10 different shapes of surface mount LEDs to see which would work the best, but I settled on a tiny SMD package, just 1.4 millimeters square. I'll get into how these are controlled later. But how do I tell if a tile's been touched or not? I considered a few options, such as perhaps a photodiode light sensor or an accelerometer. These both came with issues, though. A photodiode would respond to changes in light. However, I was unsure that touching a tile would block enough light to be distinguishable, or that sunlight streaming through a window wouldn't throw off the results. An accelerometer may have worked, but they're generally more expensive and require physical displacement to generate a signal. While I likely could have found one sensitive enough, I believe there's a better solution. I settled on a small microphone. These meet all the requirements. They're small, as evidenced by the one I'm currently holding in my fingers. They're cheap, and they should be very sensitive to perturbations. The idea is to couple each microphone to a tile. When the tile is tapped, a sound wave will be generated in the material, which will excite the microphone. I'll then find the difference between the maximum signal and the minimum signal and gauge the amplitude of the tap. Now this should fall off as a function of radius, so the tile touched should be the loudest, and those around it less loud. I'm hoping that the similar materials, like the grout between the tiles, will attenuate the sound so that it is obvious which tile has been touched. So we've got an LED and a microphone on each tile, but how do we implement it all together? Let's draw it out. Okay, so we have our tile here. To each tile we'll bond the LED with red, green, and blue components, as well as the digital control chip. We'll then attach one of these small microphones, and now we'll duplicate this over and over again for each tile. But how many tiles are there? This area is trapezoidal, with a base width of 46 1/4 inches and heights of 35 3/4 and 69 1/4 inches. Doing a quick area calculation shows a total of 2,428 square inches. Now each sheet of tile contains 16 tiles and is about 12 inches by 10.5 inches, or 126 square inches. This means only 2,428 divided by 126 tiles, or about 20 sheets of 16 tiles. That's 320 tiles, and I'm not accounting for edge cuts, so this is going to be a lot of soldering. On to how the electronics will work. First, these addressable LEDs have just 4 connections on them. There's the obvious power and ground, as well as a data input and a data output. The LEDs are strung together such that the first LED in the string has its data input connected to the output of whatever is controlling the entire string of LEDs. All LEDs after the first one have their data input connected to the data output of the LED that came before it. As such, you actually only need 3 wires to connect up an entire string of LEDs. These SK6805 LEDs, and this is generally the same for the Neopixels, such as the SK6812 and the WS2812, they require a clock signal sent to them at around 800 kHz. Now typically you'd imagine a clock signal with 50% duty cycle. That is, the amount of time the clock is high and low is symmetric. However, here we're actually going to use an asymmetric clock signal to encode the data right into the clock. To signal a logical 0, we'll send a clock that is low for 0.88 microseconds and high for 0.32 microseconds. To signal a logical 1, we'll give it a signal that is high for 0.74 microseconds and low for 0.46 microseconds. These values come straight from the datasheet for the SK6805 EC14, the exact LED I'm using. And even though the datasheet is not in English, I can at least still read these numbers. Note that both of these add up to 1.2 microseconds, the period that represents 1 clock cycle at 800 kHz. Now these values are given in the datasheet as ranges, and some of the datasheets for the SK6805s even list a tolerance on the frequency. I'll be exploiting this later to get a lower clock rate. So we've got this string of clock signals with the data encoded in them. What we need to do is send 24 bits of data representing the 8-bit values for the brightness of the green, red, and blue LEDs in the string, in that order. Each LED will block the signal from reaching the subsequent LEDs until it has had its fill of 24 bits. Basically, if we have 10 LEDs and each LED requires 24 bits, we'll need to send a total of 240 bits. The first LED will receive the signal and will record the first 24 bits it sees, all while not forward anything out of its data output. So the second LED, and all the ones after that, will hear absolutely nothing of those first 24 bits. Once the first LED has had its fill of 24 bits, it will forward anything else it gets straight through, and it won't pay attention to those bits. The second LED will then see these next 24 bits, the second 24 bits, as the first thing it sees. So it's going to do the exact same thing the first LED did. It will record the first 24 bits, it won't forward anything along during that, and then once it's had its fill of 24, it will forward anything else it sees straight through. Each LED will do this in succession, recording the first 24 bits, then passing the rest on, so that a theoretically infinite number of LEDs can be controlled off of just one wire. There are of course practical limitations, such as the power required to run infinitely many LEDs, but the number you're limited to is well in the thousands. When you're done assigning the values to the LEDs, you simply hold the clock line for 200 microseconds, hold it steady, and that tells the LEDs to reset and start the process all over again. Note that the values I've given are for the SK6805 EC14. If you're using a different LED, be sure to consult the datasheet. So now that I've handled commanding the LEDs, how do we deal with the microphones? Each microphone sends an analog signal that is a small varying voltage, perhaps just millivolts, for a given audio excitation. In general, analog signals are sensitive to external noise, parasitic capacitance and inductance, etc. So it's difficult to send them over long wires in uncontrolled environments. Besides, if I were to send each and every signal back, I would need 320 wires. And not only am I too cheap for that, but microcontrollers wouldn't have enough pins, and frankly I don't want to run all those signal wires. So here's my thought. As discussed, each LED will get its first clock signal only after each of the LEDs before it has already gotten its signal. So if I send a response back from each tile only when it gets its first clock edge, then the responses should be returned in the same order that the LEDs were commanded, as long as each response is short enough that it occurs within that 24 clock cycle span, and the signal integrity is sufficient. The main controller can then just receive the signals and know which microphone value corresponds to which tile, since they're all in order. Signal integrity is one of my main concerns here. I'm worried that the return signal will be garbled and unreadable after passing through so many circuit boards without decent impedance matching. Now this is really a topic for another video, and since I don't know how big of a problem this is going to be until I connect several boards in succession, I'm going to leave it at that for now. Implementing this technique will look like this. 2 LEDs will be implemented onto each board, with each board straddling between 2 tiles. This will save me from having to build twice as many boards. The LEDs are easy. There will just be a wire to the data input of the first LED, and a trace on the circuit board to forward that signal from the first LED onto the second. Each board will also contain 2 microphones, one to couple to each of the 2 tiles. But now I need something to monitor these microphones and report back the maximum voltage swing from them. As alluded to, a microcontroller is the obvious solution here, but even the cheapest part from a reputable company, such as ST Microelectronics, the STM32C0, is 74 cents for a quantity 250 parts. Now luckily, well, maybe luckily, this depends on your definition of luckily, I follow some electronics forums. There was recently some buzz about the cheapest microcontroller, which turned out to be a one-time programmable part for something like 3 cents. Now this wouldn't work very well for my application, because you can only write it once. And if I'm developing the code, you can bet I'm going to flash 200 or 300 attempts of software to it. Slightly after that article, however, there was talk of another part, this time a flash-based part, called the Puya PY32. Now these are Cortex M0 Plus parts, much like the STM32C0, and they're available for around 10 cents each in modest quantities. Even if I got the highest end part, a 64-pin part with substantially more RAM and program memory, it would only be 57 cents per part, still cheaper than the cheapest STM32C0. This is the perfect solution. For around 10 cents per board, I can read the microphones with the internal analog to digital converters, then I can perform the math, detect the amplitude, and use the interrupt pins connected to the LED's data line to trigger a response back to the main controller. These even have a UART peripheral, so I can use that to send the response back. Let's briefly talk about hardware selection. Every engineering project has its constraints. For electronics development, these are often things like cost, reliability, size, weight, power, development time, part availability, etc., etc., etc. Depending on what you're developing or who you're working for, these constraints can be radically different. In my day job, for instance, things like reliability and schedule tend to dominate over things like cost and size. For this project, the main drivers are cost and development time, although size is also very important, because circuit board cost is proportional to the size of the circuit board. So the smaller the board, the cheaper I can buy them, the lower the cost. As mentioned, I chose the SK6805 EC14 LED, which is tiny, thin, and should have no issue going between the tiles. For microphones, I chose the ZTS6156. These are analog output surface mount devices that are slightly smaller than 2x3 millimeters. They have their audio port on the bottom side and have an internal preamplifier, but they do require external amplification to be read directly by the microcontroller's analog to digital converter. For that amplification, I'm using a cosine COS722 dual op-amp. By using a dual op-amp, I can put only one extra part on the PCB. Finally, the microcontroller I selected is the PY32 F002 in a QFN16 package that is only 3 millimeters square. I ordered 500 of all these, and at that quantity, basically every part came out to 10 cents each. I also bought a bunch of passive components. These all came from reputable companies, and they actually ended up costing more than all of the active parts. PCB selection was something that I doodled on for a while. I wanted to mount the LEDs to the sides of the tiles, where the grout would ordinarily be. The back of the tile is opaque, and besides, if the LED was shining through the back of the tile, it would just look like a spot of light in the middle of the tile, rather than really making the whole tile glow. Originally, I thought I'd have a thin, long board that would go sideways in between the tiles, with all the components on either side of it. I quickly realized this was overly optimistic, though, because the gap between the tiles, which is supposed to be 1/8 of an inch, is actually a little under that, and there's just not sufficient room for all that. A standard PCB thickness is about 1/16 of an inch, so that only leaves about 1/16 of an inch left for components. I also had some scope creep, which meant that I needed to put more components on the circuit boards, meaning I needed more board space, so even if it would have fit in the crack, I don't think I could have put enough in that much area. I settled on flexible PCBs. My favorite low-volume vendor, Osh Park, offers these for $10 per square inch for 3 copies of a board, meaning they could be affordable as long as I keep them small. I may explore even cheaper options for PCB fabrication for the full build. With a flex PCB, I can have a large area parallel to the tiles where the bulk of the components will go. Then I'll have the LEDs out on these little arms. I'll simply flex the arms to 90 degrees, slide them in the space between tiles, and glue them in place. Some other little details. To join the PCBs, I'll be using ribbon cable. I ordered a full spool of 26 gauge 4 conductor from 3M that is only about 2/10 of an inch wide. I'll strip the insulation and solder it directly to the PCBs. There was a slight issue with voltage levels. The microphones want 1.5 to 3.6 volts, whereas the LEDs specify 3.7 to 5.5 volts. Notice that there's no overlap here. Because the current draw of the microphones is so low, however, I'm going to try to get away with just using a resistor divider to drop the 5 volts into the microphone's range. The microcontrollers actually specify 1.7 to 5.5 volts. This is actually larger than the STM32 parts, which don't tolerate 5 volts input voltage, meaning that these 10-cent parts were actually the better choice for this project. There's another question regarding microphone orientation. The microphones I've chosen have their sound port coming out the bottom, basically through the circuit board. I'm hoping to block that port off and then just couple the metal case of the microphone right to the tile. It remains to be seen if this is going to perform well enough. Okay, let's jump into KiCAD and let's take a look at the actual schematic. First, the LEDs. Not much to see here, just data in, the intermediate signal, data out. The ins and outs are over here where the ribbon cables mate. These are custom footprints I made to match the ribbon cable pitch. I added decoupling capacitors anywhere the power rails intersected apart, including the ribbon cables. Next is the microphones. They're simple, they're just a voltage in, ground, and analog out. You can see the divider here. Also note that when I calculated the resistance values for these resistors, I had to take into account the current the microphone was consuming. I couldn't just use the normal resistor divider equation, as that would have given me erroneous values. The microphone outputs feed into the dual operational amplifier. Both sides of this are identically configured, both in inverting mode. I'm using another resistor divider to set the common mode voltage to half of the 5 volt rail. There's a simple debug LED over here, and finally the microprocessor. Most of the microprocessor signals are simply run to and from their corresponding pins. I just had to make sure that the microphone signals went to 2 of the ADC channels, the LED signals went to non-conflicting interrupt pins, and the UART was in the right place. Also, don't forget to pull the boot 0 line down, or nothing is going to work. I broke the remaining pins out to small circular test pads, just in case I needed them for unforeseen reasons. I've put the serial debug connections on test points as well, so I can solder wires to them and plug it right into my debugger. Hopping over to the layout, we can see the unusual board design with the 2 arms. Each arm has LEDs on opposite sides. That way when I bend the arms to 90 degrees, the LEDs will point opposite directions, 1 into each tile. These boards are only 1 inch by 3/4 of an inch, making them 3/4 of a square inch, meaning they're going to cost me $2.50 each. The front side has the microphones, the debug LED, and the test points. Now this proved to be a bad idea, putting the connections on this side, because once I glued the circuit board onto a tile, I could no longer access any of these. The back side contains everything else. The pads for the ribbon cable, the processor, the op-amp, and nearly all of the passive components. I'm not going to go into depth into circuit board layout. It's certainly not my area of expertise, but I do find it quite enjoyable. It's an intriguing mix of engineering, art, and puzzle solving. For this board, I prioritized the important data out signal line. I kept a wide 5 volt trace since all of the current for all the LEDs in the string are going to be flowing through this trace. And I attempted to keep the analog signal lines short and clean. I also made sure that the traces and copper fill were only on one side of the arms where they're going to flex. This will help them bend easier, since I don't need to stretch or compress the copper on both sides of the board to bend the arms. So I put the order in for the circuit boards. Now there's nothing to do but wait. While we're waiting for these boards to come back, we might as well talk briefly about the software. I plan to use an STM32 development board, such as the Nucleo boards that STM themselves make, and this is going to run the entire wall. Now these are reasonably cheap, and I only need one because it will be substantially more powerful than the PY32. I enjoy working with STM32 parts. STMicroelectronics has great free tools, including an Eclipse-based IDE and a configuration tool that can handle all of the work configuring a UART or input-output pins, etc. There's also a tremendous amount of online support for these, in forums, Stack Overflow, even stuff like university lectures. This makes it very easy to get started and learn. The PY32 though, let's just say it's not exactly the same. I found out about them from Jay Carlson's blog, but that's about the only place on the internet that talks about them. I think Jay has a wee bit more experience than I do with these types of things as well, so I wanted to implement them in the simplest possible way. Now that meant I did things a little bit differently. For the IDE I chose Keel Microvision, which I believe is ARM's own IDE, and you can download a copy right from them free of charge. To get started with a board, you're going to need a pack, which I was able to get from Puya's website. Note that when you go to their website, all of the PY32 documentation is the same. It's just in the same zip file. So download it and you'll get everything you need for any of the PY32 parts. The pack is located in there if you want to install it that way. And when I originally started this, I had to manually add the pack. But the latest time I installed Microvision, I found that it was already there. In this zip file, you can also find the text documentation, and it's 90% in Chinese, although there are a couple of data sheets and reference manuals in English. Although there isn't one for the PY32F002A, there is a reference manual in English for the PY32F030, which is actually really well written and applicable, since they're both Cortex-ARM0 cores. There's also libraries for the HAL drivers, and these look very familiar to stuff you might have seen if you've worked with STM parts. And by very similar, I mean very, very similar. So once I had the pack and I linked all the libraries, I wrote some C code and everything worked perfectly. If only that were the case, because that's not true at all. All of these tools I mentioned that ST has to make everything easy, well, none of those exist for the PY32 parts. So I had to learn how to manually initialize every peripheral. Now, this isn't particularly hard. There's plenty of examples, even in the downloaded zip file you get from their website. There are good examples for each of the peripherals, and these were extremely useful. But there were some other issues I ran into. For one, I have both a knockoff ST-Link v2 programmer, as well as an official ST-Link v3. I found out the hard way that the official ST-Links are locked to STM products, so I had to use the cheaper one here. I also learned, and believe me, this wasn't easy to figure out, that even though the parts say that they're good to 5.5 volts, and indeed they seem to work fine there, they will not program at 5 volts. I had to drop the voltage to 3.3 volts in order to get the code to flash. I purchased a couple of PY32 F003 development boards, very similar to the F002, just with a few more peripherals. And by the way, all the PY32 parts, the microphones, the LEDs, and the op-amps, were all purchased from LCSC. Now these development boards were really nothing more than a breakout board with a regulator and a crystal, and I happened not to even use the crystal. So before really diving into this project, I wanted to make sure that I could get these to do anything at all, and I used these boards to do that. I implemented stuff like serial communication, I got the ADC's reading values, I was able to configure the clocks appropriately, and I verified that the interrupt pins would work. And for the most part, I was able to get everything working to my satisfaction and move forward with the project, although I was never able to get the printf redirected to the UART. If I wanted to send serial message to a computer for debugging purposes, I ended up doing it the hard way by concatenating strings in C, converting types, and then manually sending it all over the UART. I still haven't figured this out. It seems to be something fairly deep in C, and I don't know, I lost interest. Of course, there are better ways to debug than printing to the console, so it wasn't a huge loss. Now, I'll probably do a whole video on the Puya series of parts, since there's so little information out there, and 10-cent microcontrollers could have some crazy applications. Let me know if you want me to push this up in the queue. So the boards have arrived, and they're thin, they're flexible, they look exactly like what I sent out. In other words, they're perfect. To populate these with components, I need a solder-based stencil. Luckily, I have the perfect tool for this, a 50-watt fiber laser engraver. Now this is meant for marking metals, but it has no problem cutting through thin ones. I have absolutely no reason to own this laser. It's very expensive, I just think they're cool, and making solder paste stencils is actually one of the main reasons I use to justify it. You can buy solder paste stencils, even cut out of metal, for literally tens of dollars. This machine will never pay for itself. So I exported the appropriate KiCAD layout data as a scalable vector graphic, an SVG file, deleted the things I didn't want in Inkscape, and then I added a few little tabs back in. I did this for both sides of the circuit board, and then I brought it over to the laser. I used Lightburn here, so I just opened that up. I applied the power and speed settings for the material I'm using, an 8,000th of an inch thick aluminum business card. Now this is too thick. and it resulted in way too much solder, but it worked fine for the prototype. I didn't grab the audio from the laser, but this is actually a laser cutting in real time. So now, I just align the board to the stencil, tape it on, spread the solder paste in, all of which is easier said than done. I'm using bismuth-based solder paste here, which melts at a very low temperature, around 138 Celsius. I usually use SN100C for conventional soldering, but I find that this low temperature stuff works really well for LEDs, as those can melt pretty easily. I'll then peel the stencil off, fix any solder paste areas that need it, and pop the components on. Throw this into the oven real quick. I'm using a Control 3 that I built from a kit out of a toaster oven. Now the kit's about $300, which does seem like a lot, but I believe these ovens work substantially better than some of the other low-cost options, and you do get quite a complete kit for the money. I already have the profile set up, so all I have to do is hit start. Now rinse and repeat for the other side of the board, and we're done. Well, almost done. I had a couple of minor issues to fix. For one, there was too much solder on some of the components, particularly on the thermal pad under the microcontroller, and this caused some of the pins on the microcontroller to lift up and not connect. I removed this part with a hot air pen, removed some of the solder with the soldering iron, and popped it back down. I also had some solder bridges on the op-amp that needed correcting, and one of the parts was in backwards, which was probably due to my laziness with the silkscreen. I reworked this by hand off camera. I'd like to put out a video at some point on some of the more advanced soldering techniques, some that you can do cheaply and effectively in the home shop, and we'll cover all of this in more detail. With the boards built, there was nothing left to do but apply power and do a smoke check. I started with the LEDs, since these didn't require me to code anything on the PY32 microcontroller, and they worked great. I then brought up the PY32 microcontroller, I checked out the ADCs, the interrupt, etc., but I think this video is going on a little too long to start talking about the software. Join me in the next one, and we'll talk about it in detail. Now this project has been tons of fun already. I've learned a crazy amount, and that's one of the best parts of doing these projects. But there's still so much to do. I need to get the PY32 code polished. I'm still having some issues with the microphones that I need to run down. And I need to take what I've learned with the prototype and design the actual final circuit board. Not to mention I need to solder at least 160 of these things, glue everything on the tile, and wire them up. Then there's the coding of the controller to command the LEDs, and programming the functions to do cool things like make ripples. Oh, I forgot about actually tiling the wall. So if you're enjoying this project and like the video, please consider subscribing. We're going to be finishing this project up, and then there are many more projects in the queue covering a wide variety of topics. Thanks for watching, and go make something.